Good morning, dear students. Today we are going to solve October-November 2015 2-1 paper. It's a theory paper. The course we are studying is Physics 5054. And let's start today's task. Question number 1 is on your screen. And remember, in this video, we will be only solving section A of this paper. Section B of this paper, we will solve in another video. Figure 1.1 shows an archer firing an arrow at a target during a competition. So here we have a bow, bowstring, arrow, archer, and target. He says let me reduce the size so you can see the whole thing. Okay. The arrow has a mass of 0.018 kg and is initially at rest. The arrow leaves the bow 0.011 second after the bowstring is released. When it leaves the bow, the velocity of the arrow is 95 meters per second. Calculate the average acceleration of arrow during the 0.011 second. So here the question is, what is the acceleration of the arrow? The initial velocity of the arrow was 0. And the final velocity of the arrow is 95 meters per second. And the time for this change in velocity, the time taken is 0.011 second. So we can very easily find out the acceleration. You know, the formula for the acceleration is change in velocity divided by time. Acceleration is equals to v minus u divided by t. So it will be 95 minus 0 divided by 0.011 equals to 95 divided by 0.011, and the answer will be 8.6 expo 3 meter per second square. It's a 2-mark numerical. I have done this on a paper. Let me show you that. On your screen, you can see question number A, first part. A is equals to v minus u divided by t equals to the final velocity is 95 minus initial velocity is 0 divided by the time taken for this change, 0.011 equals to 95 divided by 0.011 equals to 8.6 expo 3 meter per second square. It's a 2-mark numerical. I hope that you have understood it. It's easy. Okay. Let's move to the next part. The next part on your screen is the average force exerted on the arrow during the 0.011 second. Now, we know the mass of the arrow, and we also know the acceleration which was produced in the arrow, and he wants us to find out the resultant force or force exerted on the arrow. So we can find out that by using the Newton's second law of motion. Its mathematical form is F is equals to ma. F equals to ma, and by applying the formula F equals to ma, and the mass is 0.018 kg, and the acceleration is 8.6 expo 3, and the answer will be 155.45 Newton. It's a 2 marks numerical. I have done this on a paper. Let me show you my working. On your screen, you can see question number 2, question number 1, part A, part 2. F is equals to ma equals to 0.018 into 8.6 expo 3. You multiply it on the calculator, and the answer will be 155.45 Newton. It's a 2 marks numerical. Easy. I hope you have understood it. Okay, let's move to the next part. He says, B part of question number 1. In practice, the force exerted on the arrow gradually decreases to 0 during firing. On the figure 1.2, sketch a possible speed time graph for the arrow as it is being fired. You see, when the arrow leaves the bow, the force on it starts decreasing. So at the start, so the graph for which the graph is between the speed and the time, and we know that because the supply of the force on it has been stopped. They gave it force and then they stopped it. So the arrow was initially at the rest, and gradually it got to the 95. And okay, so what we will do, the force, we will draw a speed time graph, and we know that our arrow moved from 0 meter per second speed to 95 meter per second speed in 0.011 seconds. So our graph will be a decreasing curve. It will be a decreasing curve. Okay. So let me show you. I have drawn this on a paper. Let me show you my work. Okay, on your screen, I hope you can see that. Okay, here we go. Here I have drawn that graph. The graph should look like this. The speed time graph should be a decreasing curve. Okay, I hope you understand. Okay, the next question on your screen is question number 2. Figure 2.1 shows a freezer for keeping food frozen. The outside surface of the freezer is painted white. Explain one advantage of having the outside surface of the freezer painted white. Okay, there we have a deep freezer, and the outer surface of the deep freezer is, normally of the white color. The reason is that the white color is a bad absorber of infrared radiation. So because it is bad absorber of infrared radiation, that's why it will absorb very small amount of heat from the surrounding. The interior of the deep freezer will be very cold, and we believe that the surrounding will be hotter. So if the outer side of the deep freezer is painted white, because the white color is a bad absorber of infrared radiation, it will absorb very small amount of heat from the surrounding. It's a 2-mark question, and I have written its answer also. Let me show you my answer. Okay. So let me increase the size and show you. Okay. So question number 2, part A, is on your screen. White is bad absorber of infrared radiation, so the amount of heat absorbed by freezer will be reduced when you color it white. The amount of heat normally it was supposed to absorb from the surrounding will reduce. It will absorb very small amount of heat from the surrounding. So that's the benefit. That's why we always paint the outer body of the deep freezer white. Okay, let's see what's the next part of this question number 2, part B. First part is B's first part is the lid of the freezer is closed and the air at the room temperature is trapped inside the freezer. The freezer is switched on. State and explain using ideas about molecules what happens to the pressure of the air in the freezer as it cools. For example, if the air is trapped inside the freezer and you close its lid and you switch on the freezer will start cooling. So the air inside the freezer, its temperature will stop dropping. So when the temperature will drop, what will happen? The the average kinetic energy of the air molecules inside the freezer, that will decrease, which means that the air molecules are now moving at slow speed. So because they are moving at slower speed, now their collision frequency with the walls of the freezer, that will decrease. So now there will be less number of collisions with the wall per unit time. So the force exerted on the unit area will decrease. That's why the pressure of the air molecules inside the freezer, when the temperature of the freezer drops, the pressure of that air inside the freezer also drops. I have written this answer also on a paper. Let me show you that. It's a 3-mark question. And here we go. Question number 2, first part. Volume as of gas inside freezer is constant. When temperature drops, the average kinetic energy of air molecules decreases. They move slower now. Their collision frequency with walls decreases, and they exert less force when they collide with walls of the freezer. So these are the reasons. One thing, their collision frequency has dropped. Second thing, now they are colliding and they are exerting less force on the wall. Okay, so the pressure of the air inside the freezer that decreases. I hope you have understood. Okay, Ji? Okay, now we are moving to the B, second part. When the freezer reaches its operating temperature, it is more difficult to open the lid. Explain why. You see, it's a very simple thing. Now you have a freezer and there is air inside the freezer and there is air outside the freezer. The air outside the freezer is have a pressure, we call it the atmospheric pressure, and that is acting downward. Inside the freezer, the air inside the freezer is also, it also has this pressure, but we have already learned in the B first part that the air inside the freezer, its pressure drops. Now the inside, so there is a difference of the pressure in the outside air and the inside air. The outer air, the atmospheric pressure, is more as compared to the pressure of the air inside the freezer. So due to the difference of the pressure in the outside air and the inside air, there is a resultant force acting downward on the lid of the freezer. So due to that resultant force, it becomes difficult to open the lid of the deep freezer. Okay, let me read my answer. I have also written this answer. So I hope you can see question number 2B, second part, is on your screen. It says the pressure of air inside freezer becomes lower than outside atmospheric pressure. Due to difference of pressure, a resultant downward force acts on lid of freezer. Due to this, it is more difficult to open the lid when freezer reaches its operating temperature. I hope that you have understood it. Okay, let's move to the next question. That's question number 3. Okay. A lorry of mass 4.4 expo 4 kg travels along a straight horizontal road at 2 meters per second. Calculate the kinetic energy of the lorry. You know, the kinetic energy of the lorry can be found by the formula 1/2 mv square, half mv square. So we know the mass, we know the velocity, so we can calculate the kinetic energy. So we will put the values and we will do the calculation. It's a 3 marks numerical. I have done this on a paper. Let me show you my work also. Okay. So question number 3A part is on your screen. You can see it clearly. Kinetic energy is equals to 1/2 mv square, and 1/2 mass is 4.4 expo 4 kg, and the speed is 20 meters per second. But I have to write square also because on the formula there is a square on the velocity. So the answer will be 8.8 expo 6 joules. It's a 3 marks numerical. It's easy. I hope you have understood it. Okay. The next question they are asking is, the lorry driver sees an obstruction ahead and applies the brakes. The lorry slows down and stops. The lorry stops a distance of 40 meters from where the driver first applies the brakes. As it slows down, the kinetic energy of the lorry decreases to zero. The kinetic energy decreases as work is done by braking force exerted on the lorry. State the formula that relates the work done to the braking force. So the work done by the braking force is equals to the braking force multiplied by the distance moved by the vehicle when the brakes are applied, after the brakes are applied. So the formula is F multiplied D. The next question, so one more question, I will show it my work also, but let's move to the next part. It says calculate the braking force exerted on the lorry. The work done by the braking force is equals to the change in the kinetic energy. You change the kinetic energy from 8.8 expo 6 joules to 0. That's the function of the brake. It made the kinetic energy of the body from 8.8 expo 6 joules to 0. So the work done by the braking force is equals to change in the kinetic energy, and it is also equals to F multiplied D. So we will write the formula that the work done is equals to 8.8 into 10 raised power 6, because the work done by the braking force is equals to the change in the kinetic energy. And I will make it equals to F into D, where F is the braking force and D is the distance covered after applying the brakes. And the distance covered is 40 meters. So it will be 8.8 expo 6 into equals to F into 40, and F will be equals to 8.8 expo 6 divided by 40, and the value of the F will be 2.2 expo 5 Newton. It's a 2 marks numerical. I have done this on a paper. Let me show you my work also. Okay, so here is the first part. Work done is equals to braking force into distance covered after applying brakes. So work is equals to F into D, and the work is equals to F into D, and we know that the work done by the braking force is equals to the work done to change the kinetic energy. So change in kinetic energy equals to 1. Work done. So in the work done in the place of the work done, I have substituted the value of the kinetic energy, which is 8.8 into 10 raised power 6 equals to F into 40, and F is equals to 8.8 expo 6 divided by 40, and the F is 2.2 expo 5 Newton. It's a 2 marks numerical. I hope that you have understood, especially that the idea that the work done by the braking force is equals to the change in the kinetic energy. The kinetic energy change from 8.8 into 10 raised power 6 to 0. Okay, let's move to the next question. Okay, question number 4 is on your screen. Figure 4.1 shows a screwdriver of mass 64 gram resting in equilibrium on a pivot. On figure 4.1, mark and label with a C the center of mass of the screwdriver. You see, there is no extra weight hung on left side or right side. So the whole screwdriver is balanced on a single point where you have put a pivot under that point. So that point where the weight of the body can be supported. The point in the body or outside the body where the weight of the body can be supported, that is the point where the center of the mass of the body is lying. So the center of the mass of the body is right at the here where the tip of the pivot is here. So I will put a dot here and I will label this thing as C. It's a 1 mark question. Okay. Let me show you and my diagram. I have done this on the diagram also. Okay. So you see this diagram. So right above the pivot, I put a dot, and that is, and I labeled it C. This is the center of mass. Okay, it's a 1 mark question. Okay, the gravitational field strength is 10 Newton per kg. Calculate the weight of the screwdriver. You know, weight formula is mg. weight is equals to mg, but the m must be in kg. The weight, the mass of the screwdriver is given, that's 64 gram, but we don't use in the weight formula the mass as grams. We convert them into kg. So divide 64 with 1000. So when you divide 64 with 1000, you will get 0.064 kg, and you multiply it with the g value, which is 10, and you will get the answer 0.64 Newton. I have done this work also. Let me show you my work. And here in the B part, you can see W is equals to mg equals to, here I am converting, I divided 64 with 1000. The reason is I want to convert grams into kg. And I multiply it with the g value, which is 10 meter per second square, or you can say 10 Newton per kg. And the answer is 0.64 Newton. It's a 1 mark numerical. Very easy, very famous question. I hope you have understood. Okay, in the B second part, he says on the figure 4.1, draw an arrow labeled W to represent the weight of the screwdriver. So you see, this is the screwdriver. Here's the center of the mass. So here I will have to draw an arrow to show that how the weight is acting. So I will draw here an arrow downward, and I will here write W, which means that it is weight. I have done this on that figure. On your screen, you can see here I have drawn an arrow, and because where is the center of the mass, from there I have drawn the arrow. The weight is acting there, and I have labeled it as W, weight. It's a 1 mark question. I hope you understand. Okay. The next part, C, is on your screen. State two conditions that apply when an object is in equilibrium. You see, whenever an object is in equilibrium, so there are two conditions, and they both are supposed to be fulfilled. And whenever a body is in equilibrium, the resultant of all the forces acting on it must be zero. The net force must be zero. This is the first condition. And the second condition for a body to be in equilibrium is that the sum of the moments acting on the body, that should also be zero. So the first condition is that the sum of the forces should be zero. And the second condition is that the sum of the moments acting on the body should be zero. So these are the two conditions for a body to be in equilibrium. It's a 2-mark question. I have written this answer also. Let me show you my answers. And where goes question number? Yeah, here we go. On your screen, you can see question number C, first part. These are first and second part. These are the two conditions for equilibrium. The first one is the net force on the object must be zero for the object to be in equilibrium. And the second condition is sum of clockwise moment and anti-clockwise moment should be zero for the body to be in equilibrium. So these are the two conditions for the body to be in equilibrium. I hope you understand, and you will also remember this. Okay, so we are moving to the next question. It's question number 5. In a steam cleaner, water is heated to its boiling point and is then turned into steam water in the gas state. So define the boiling point. Boiling point is the temperature at which the liquid is converted into gas, and the temperature during that whole process remains constant. That temperature is called boiling point. It's a definition. I have written this definition also, 1-mark definition it is. Okay, so A part on question number 5 on your screen. The temperature at which a liquid converts into gas and temperature remain constant until all liquid is converted into gas. That temperature is known as boiling point. I hope you have understood it. And it's a definition. Please remember these definitions. Question number 5, B part. Describe the molecular structure of a liquid. So it's a 2-mark question. We have to define How are the molecules arranged in a liquid? It's a famous question of physics in O levels physics. Sometimes they will ask you what is the molecular structure of liquid. Sometimes they ask you what is the molecular structure of gas. Sometimes they ask you what is the molecular structure of solid. But this time they are asking for the molecular structure of the liquid. I have written this answer, and we can read it from there. Liquid molecules are close together with no regular arrangements. Molecules in liquid vibrate, move about, and slide past each other. The main question was about the arrangement, but I have also added a sentence about the motion of the molecules. Okay, so remember these words. You can also read from your textbook, Physics Matter, or if you have any other textbook, and see what is the structure of the liquid molecules. A very important question. Okay. Next question he's asking is explain using ideas about molecules why thermal energy heat must be supplied to water as it boils. And we are assuming that he's talking about the water when it is at its boiling point. So you see, when the water is at its boiling point, but it's converting into gas, still you have to provide the energy. But that energy is not used to raise the temperature. So for what purpose that energy is used? Why we need the energy during the process of the boiling? And what that energy perform, that is the question. So you see, the energy which you provide during the boiling, that is used to overcome the intermolecular forces. It is used to break the intermolecular bonds. It is used to move the molecules away from each other. It is also used to overcome the atmospheric pressures. So remember these sentences. Question number two, the second part is a 2-mark question. I have written this answer also. Let me show you on your screen. The second part. Energy is used to overcome intermolecular forces and break intermolecular bonds and move molecules away from each other. Energy is also needed to overcome atmospheric pressure. So the energy which you providing during the boiling is used to do these things. It's a 2 marks question. So my dear students, I hope that you have understood. Okay. Now we are moving to question number 6. A burning candle is placed close to a thin converging lens. The candle acts as the object. A white vertical screen is moved to a position on the other side of the lens from the candle. Figure 6.1 is a full-scale diagram on graph paper of the lens and the screen. Okay. Let me reduce the size so you can see that. So here we have a lens. This is the optical center of the lens, and here they have put a screen. If I will increase the size, you will be able to see it. And here is the image of the candle. This is the principal axis. This is the image of the candle, and it is inverted, means the image formed is real. And he says the focal length of the lens is 2.4 centimeter. The screen is 7.2 centimeter from the center of the lens. A sharply focused inverted image of the candle is produced on the screen as shown in the figure 6.1. The first question is define the term focal length. Define the term focal length. So he wants us to define the term focal length. Okay, so we can define focal length. Focal length is basically the distance on the principal axis from the optical center to the principal focus. On the principal axis, the distance between the optical center of the lens and the principal focus, that distance is known as focal length. I have written this definition, 1-mark definition. I have written this definition. So on your screen, you can see, I hope you can see that horizontal distance between the optical center of lens and the principal focus is called focal length. Horizontal distance between optical center of lens and principal focus is called focal length. Uh, I hope you have understood. Okay, well, let's move to the next question. Is question number B, first part on the figure 6.1. Mark and label with an F each of the two focal points, principal foci of the lens. Okay, so if you have the lens, so the principal focus are on both sides, on this side and also on this side. So from the lens, he said that the focal length is 2.4 centimeter. So from the lens, put a scale or with the help from, because it's the real diagram is made on the graph paper, and five small squares are representing 1 centimeter. So he said that 2.4 centimeter on this side, put a dot on the principal axis, write F there, and 2.5 centimeter on this side of the lens. On the principal axis, put a dot and mark it as F. So you will mark both F on the left side and on the right side of the lens. 2.4 centimeter from the optical center. 2.4 centimeter on that graph paper. If you have the actual paper in front of you, then you will count five small squares, and two small squares. So it will be 2.5. So five small squares are representing 1 centimeter on that original diagram. So if you have marked F on both the sides, then you are good to go. Okay, the B part is the point Y is the tip of the image. On figure 6.1, draw a ray diagram to locate the position of the top of the object. Label this point as X. Using the figure 6. Next question is using the figure 6.1, determine the distance of the candle from the center of the lens. So let me show you. I have drawn this a full scale diagram of this candle on a paper, and let me show you that. Let's reduce the size a little bit so you can clearly see. Oh, still need to reduce the size. Okay. So you see here, this horizontal line is representing the principal axis. It's a full scale diagram. Okay. So this black line here represents the lens, and this red line here represents the screen. So first of all, I have drawn this lens, and then on a distance of 7.2, I marked here, and I drawn a screen with the red color. And on the screen, there was an image of candle, and I have noted what is the length of the candle and the length and the image of the candle, I mean. And this is a full scale diagram. So the first thing he asked us was to mark F on both the sides of the lens. So at 2.4 centimeter distance, I marked this F, and 2.4 centimeter on this side, I marked this F. Remember one thing: when you are working on a graph paper, and the graph paper was provided by the examiner, and already the diagram was already there. So now you will count the squares, not put a scale there and start measuring with the help of the scale. Do the counting on the graph paper by counting the squares. Okay, so I mark 2.4 centimeter by counting the squares, not by measuring with the scale. So be careful in this manner. Okay, the next question was to draw the ray diagram. So what I will do, this is the tip of the image. I will join it with the F, and I will use the scale, and I will draw this line until it touch the lens. With the help of the scale, join the arrowhead of the image with the F, and prolong this line till the lens. Once you touch the lens, then you will draw a line parallel to the principal axis on the left side of the lens. Then what I did, I joined the top of the lens, image of the lens, on top of the image of the candle, I mean, and this was the arrowhead here. I joined it with the optical center of the lens with the help of a scale, and I prolonged this line. Where these two lines intersect each other, that is the tip of the object. That is the arrowhead of the object. So I have drawn the object here, the candle here, and this top I will label it as X. I hope that you are able to understand how this ray diagram we have drawn. And if you have an actual paper in front of you, then it will be much easier. Okay, and another thing he's asking, what is the distance of the object from the optical center? So measure how much is this distance. But you are not supposed to measure it with the scale. You will count the squares horizontally, and then you can tell what is the distance. So my calculation is it's approximately 3.4 centimeter. I hope everybody understands this now. Let's move to the next question. The next question on your screen is question 7. Audible sound waves and ultrasound waves both consist of compressions and rarefactions. Describe one difference between a compression and a rarefaction. In the compression, the molecules of the medium, they are very close to each other, and the pressure is very high. Whereas in the rarefaction, the molecules of the medium are the distance between those molecules is larger. They are away from each other, and the pressure is low. So let me read my answer. I have written this answer also. Okay, on your screen, can you see that question number 7, A part on your screen? In a compression, particles of medium are closer to each other than they are in a rarefaction. Pressure is higher in a compression than in a rarefaction. I hope you know this comparison by now, and you will remember this. Okay. Question number 7, B part is on your screen. In a particular medium, the speed of both the audible sound and ultrasound wave is V. State the equation that relates the wavelength lambda of a sound wave to its frequency f. The relationship between the frequency, speed, and the wavelength is, we call it the wave equation. V is equals to F lambda. V equals to F lambda. I have written that equation. Let me show you that. Yeah, this is that equation. V is equals to F lambda. V is equals to F lambda. I hope you know this. Sorry. Okay, next question is explain how in this medium the wavelength of an audible sound wave compares with the wavelength of an ultrasound wave. He has given us already two conditions. One condition is that both the ultrasound and a normal audible sound, they are in the same medium. Plus, they both have the same speed in that medium. Now, when they have the same speed, so the velocity of both the sound waves is same. And we know that the frequency of the audible sound is lower and the frequency of the ultrasound is higher comparative to each other. So we know that the velocity is the product of frequency and the wavelength. If the velocities are supposed to be the same and the audible sound has lower frequency, and because the velocity is the product of the velocity, so frequency and the wavelength, so its wavelength will be naturally longer, larger. And the ultrasound, if it has the same velocity, and we know that the velocity is the product of the frequency and the wavelength, And because the ultrasound has higher frequency, so its wavelength will be lower. It will have smaller wavelength. I've written this answer also. I have tried to explain to you this. It's a little confusing concept. Wavelength of audible sound will be longer than ultrasound because in this medium, this particular medium, their velocity is same, but audible sound has less frequency than ultrasound. Because the frequency is less, so its wavelength will be more to give the same velocity, and velocity is v is equal to f lambda. I hope that you have understood this. It's a little tricky thing. Describe one use of ultrasound waves. Ultrasound waves have many uses. One use is the prenatal scanning, and another use of ultrasound is the cleaning of the jewelry. Here, I will be giving an example on cleaning of the jewelry. What we do, we take a cleaning solution in a bowl and we put the jewelry in it, and then we transmit ultrasounds in that cleaning liquid. So due to very high frequency of the vibrations, and the dust particles from the jewelry are dislodged and the jewelry becomes very clean. So this is how the ultrasound waves are used for cleaning the jewelry. I've written this answer also on a paper. Let me show you that. Okay, question number, I hope you can see. Okay, question number 7C part. Ultrasounds are used to clean jewelry. Jewelry is dipped in cleaning solution. Ultrasounds are transmitted into cleaning solution. Due to very high frequency of vibrations, dust particles from jewelry are dislodged. So this is how you do the cleaning of the jewelry with the help of the ultrasounds. I hope that you have understood this. It was a 2-mark question. So, okay. So here we go. Question number 8 is on your screen. A potential divider is made from a light-dependent resistor LDR and a 6K ohm fixed resistor. The potential divider is connected in series with a 12-volt DC power supply, and a voltmeter is connected across the 6 kilo ohm resistor. Figure 8.1 is the circuit diagram. You see, it's a typical potential divider, and this LDR is on the position of R1, and this fixed resistor is on the position of R2, and we have put a voltmeter across R2. So we call, if you study that topic in your book on the potential divider, we call it as V out. This is called the voltage of the battery. And remember that formula, before you go into the question, remember that formula. The V out is equals to R2 divided by R1 plus R2, the whole thing multiplied with voltage of the battery. We will use this formula and this concept. So it's a potential divider. He says the light shines on the LDR. The resistance of the LDR is 2 kilo ohm. Calculate the current in the LDR. Now you see here what happened. They are shining light on the LDR. So the LDR's resistance is 2 kilo ohm. So what is the total resistance of this whole thing? So this is 2 kilo ohm. This is 6 kilo ohm. And they are connected in series with each other. So we can find the resistance of these two. We can find the resistance of these two. How? They are connected in series. So R equivalent will be equals to R1 plus R2. So 2000 ohm plus 6000 ohm, and the answer will be 8000 ohm. So I know the total resistance of the circuit. I know the EMF of the battery. So I can calculate how much current is coming from the battery. The current coming from the battery, the formula is EMF divided by the total resistance of the circuit. So the EMF of the battery is 12 volt divided by The total resistance of the circuit is 8000 ohm. So 12 divided by 8000 and the answer will be 1.5 expo minus 3 ohm. So the current from the battery will be 1.5 expo minus 3 ohm amperes. It will be ampere. Sorry, I said ohm. It will be ampere. So that current will come out of the battery. So because it's a series circuit, they all are connected in series with each other. So the current which come out of the battery, the same current will flow through the LDR and the same current will flow through the fixed resistor. So the current through the LDR will be 1.5 expo minus 3 ampere. Let me show you my working. This is a 2 marks numerical. Uh, okay, on your screen you can see the current from the battery is equals to EMF divided by R1 plus R2. So it will be 12 divided by 2000 plus 6000, and it will be 12 divided by 8000, and the answer will be 1.5 expo minus 3. By mistake here I have put a ohm sign. Don't put ohm sign here. It was amps. A. Put a A here. Amps. So due to this 10 raised to power minus 3, I will say 1.5 milliamps. This unit I wrote by mistake. Here it should be a capital A. Milliamps. Correct this thing. Okay. I'm sorry I made a mistake. In a little bit mistakes can be done by a human. So the answer is 1.5 milliamp. M, small m, and capital A. I hope you will rectify this when you are working. Okay. Okay. So the next question is the reading on the voltmeter. This is that famous formula of the potential divider. This reading on the voltmeter, you know, this voltmeter is across R2. So V out, we call it V out in the when we study potential dividers. So the famous formula is on the screen. V out is equals to R2 divided by R1 plus R2 into the voltage of the battery. R2 is 6000 divided by R1 is 2000, 2000 plus 6000 into 12. So the answer will be, if you do the calculation, the answer will be 9 volt. So the reading on the voltmeter will be 9 volt. The V out reading will be 9 volt. It's a 1 mark numerical. And don't forget this formula about the potential divider. R2 divided by R1 plus R2 into V of the battery. Okay. Then another question, B part. The brightness of the light on the LDR is gradually increased. State and explain what happens to the reading on the voltmeter. Remember this statement. I will show you the diagram. He says the brightness on the LDR has increased. When the brightness on the LDR increases, the resistance of the LDR starts decreasing. When the brightness on the LDR increases, the resistance of the LDR drops. Because the resistance of the LDR drops, what happens? It starts dropping less voltage. It will take less voltage. When it will take less voltage, this thing will, the fixed resistor will take more voltages. Because from the battery 12 volts are coming and the 12 volts are supposed to be consumed. So if the LDR will take less voltage, then the fixed resistor will have to take more voltages. So the reading on the, because the voltmeter is across the fixed resistor, so if the LDR will take less voltage, the fixed resistor will take more voltages and the voltmeter will show a larger reading. The reading on the voltmeter will increase. It's a 2 mark question. Let me read you my answer. I've written this answer also. Question number is B part is on your screen. When light on LDR increases, its resistance decreases. So voltage drop across LDR decreases and voltage drop across fixed resistor will increase. So the reading on the voltmeter will be higher. It's a 2 marks question. I hope that you have understood the concept. Okay, sir, we have C part. He says suggest a use for a potential divider made from an LDR and a fixed resistor. So we have to give a practical use of this thing. You know, when this will be in the bright light, the reading on the voltmeter will be higher, and when this thing will be in the darkness, the reading on the voltmeter will be low. So this voltmeter reading can be calibrated, and this whole assembly can be used as a photometer. Photometer is device which tells us how much is the light. You must have seen photometers in the umpires have in cricket match. So whenever a batsman complains that I'm not able to see the ball because the light is not enough, so what he do, he takes out a meter and checks how much is the light. So that is called a photometer. So this can be used as a photometer because when it will be in the bright light, the reading on the voltmeter will be high. So it will mean that the light is bright, and when it is exposed to dark light, it's in the dark or the light is less, then the reading on the voltmeter is less. So this thing can be used as a photometer. Let me read you my answer. This can be used to make a photometer. It's one mark question. Okay, dear students, by this question, we have came to the end of the A section. After after this, the B section starts. In this video, we were only attempting the A section of October-November 2015 paper, and it was paper number 2-1. The course we are studying, Physics 5054. It's section B. We will solve in another video. I hope that I am a little bit help to you. If you will be keep on working hard, and you keep on reading, and you keep on watching different teachers videos, and continue writing the answer, your answering skills will improve, and your grades will also improve. I once again I want to thank you everybody, and have a good